8, we have this new definition of a derivative function, and it's in terms of some limit, and it ends with provided this limit exists. And so today we consider when that limit might exist and when it might not exist. And not to spoil the surprise, but when it does exist, we'll say that the function is differentiable, and when it doesn't, we'll say that it is not differentiable. Which is to say that we'll call a function f differentiable at a particular point a if f prime of a exists, if the derivative at that point a exists. And here we are reverting to our previous definition of the derivative of a function at a particular point. And so what we're talking about is when this limit, the limit as h approaches 0, of f of a plus h minus f of a all over h, if that limit exists, then the function is differentiable at the point a. And we'll often be interested in saying that a function is differentiable over some given interval. What does that mean? Just that it's differentiable at every single point in the interval. And let's start with the classic example, f of x is equal to the absolute value of x. And I've sketched a quick graph of the absolute value of x over on the right. And we can ask ourselves the interesting question, what is f prime of 0? What is the derivative of this function at x equals 0? Well, by definition, that derivative is the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. And that's the limit as h approaches 0 of the absolute value of 0 plus h minus the absolute value of 0 all over h, which of course simplifies to the limit as h approaches 0 of the absolute value of h over h. And then the question becomes, does this limit exist? Well, just like any two-sided limit, it exists if and only if the one-sided limits both exist and give the same value. And so we have to consider the limit as h approaches 0 from the left of absolute value of h over h, and the limit as h approaches 0 from the right of absolute value of h over h. Now as h approaches 0 from the left, think of small numbers close to 0 but to the left of 0, like negative 1/100th, for example. Well, you get the absolute value of negative 1/100th over negative 1/100th, and the absolute value of negative 1/100th is positive 1/100th, divided by negative 1/100th is negative 1. And for any number that you choose that's close to 0 but to the left of 0, that same exact thing happens, where you have the same number in the numerator and the denominator, except the one in the denominator is negative and the one in the numerator is positive. And so the limit as h approaches 0 from the left is negative 1. On the other hand, as h approaches 0 from the right, we'll take a very small number like 1/1,000,000th, for example. Absolute value of 1/1,000,000th is 1/1,000,000th. And so you have 1/1,000,000th in the numerator and 1/1,000,000th in the denominator. They're both positive. And when you divide the same number by itself, you get a positive 1. And so the limit from the left and the limit from the right are not the same. And so this two-sided limit does not exist. Which is to say that the function f of x equals the absolute value of x is not differentiable at x equals 0. None of these things, the limit from the left, the limit from the right, or the fact that it's not differentiable at 0 should come as a surprise, really, because the derivative at 0 ought to be the slope of a tangent line at 0. And what is a tangent line at 0? Well, if we're approaching 0 from the left, if we're looking at secant lines from the left, well, then we get this as our tangent line. So as a secant line for some value, close to 0 from the left. And notice that's a line with slope negative 1. That tells us why this limit is negative 1. On the other hand, pick some value to the right of 0 and draw a secant line there to try to get an approximation of the tangent. And you get this line right here, which has a slope of positive 1. And so the slope of a secant line approaching from the right is positive 1. And so what would a secant line at 0 look like? Well, there isn't one, because there's two different things happening depending on whether you're coming in from the left or the right. By the argument we just gave, this function f of x is the absolute value of x absolutely is differentiable everywhere else, because anywhere else there's a tangent line. The tangent line, if you're to the right of 0, has slope 1. The tangent line to the left of 0 has slope -1. And so yeah, there's a derivative at every other point, just not at x equals 0. There are really only 3 ways that a function can fail to be differentiable, and I'm going to show you each of them very, very quickly right now, just as quick graphs. And the first is just what we just saw with the absolute value. The function can have some sort of angular spot, like right there. This function differentiable everywhere except at whatever that x value is, because as you come in from the left, you get a completely different tangent line than you would as you come in from the right. So not differentiable wherever there's some nasty little angle like that in the curve. This is sort of the most common reason that a function is not differentiable. The second, any place a function's not continuous, it's not differentiable. And the reason is, if you look at what a secant line would look like, well, imagine a secant line coming into this point, say, from right over here. Well, it looks something like that. And then if you got a little closer, it looks something like that. And we're approaching some sort of line that looks something like that. But what happens if you come in from the left? Well, now a secant line looks like that, or like that. And then even closer, it looks like that, and completely different. And so the limit from the left, clearly not equal to the limit from the right. Something very similar is happening to the graph over here, except, well, if you come in from the left, you get a line something like this. And the closer you get to this point, the more vertical the secant line becomes. And the same thing is happening if you're coming in from the right. But what we're approaching is a completely vertical secant line. And so the tangent at that point would be vertical, and so the limit would be infinity, because vertical lines have slope infinity. And so in order for the limit to exist, it has to exist as a real number. And so that tells us that any place that a function is not continuous, then it's also not differentiable. And the last way is a little bit subtle. It's possible that there could be a point on a function where a tangent line is completely vertical, in which case the derivative at that point would be the slope of that tangent line, or infinity, and so once again, the derivative doesn't exist because the limit has to exist as a real number. Okay, I just want to tack on very quickly one sort of stupid pet trick with derivatives that is popular amongst calculus teachers, and that is, given the graph of a function, what does the graph of its derivative look like? And there'll be a few homework problems like this. It's not the most important topic, but it does help you perhaps understand what the derivative is a little bit better. That's the idea. So we'll just do a quick example, and then you'll be ready for your homework. Okay, here's some graph f of x, and we're going to try to sketch the graph of its derivative. How are we going to do it? We're going to pick some x values, and at each of those x values, we're going to try to estimate the slope of a tangent line to this curve. And whatever we get as a slope for the tangent line, that'll be the value of the derivative at that point. Let's do a couple and you'll see what I mean. So we'll look at this point right here, and we'll try to sketch a tangent line. And a tangent line looks something like that. And what's the slope of that line? Well, I don't know, but it's some positive number. And, it's not, assuming that this has like an equal scale in both directions, it's not a billion. A billion is very steep. And it's not, a tenth. A tenth is very small. And, a slope of 1 is like a 45-degree angle. So it's some number a little bit bigger than 1. Maybe it's 2. Maybe it's 1.5. I don't know. We make a guess. So there's my guess, somewhere between 1 and 2. What happens at x equals 0? Well, a tangent line at x equals 0, still a positive number, but a smaller positive number. Look, if you look at the slope of that line, still positive. It's increasing as you're going from left to right, but it's not increasing as steeply as the one before it. So at 0, we get a smaller number, smaller positive number. Is it 1? I don't know. Maybe that's a 45-degree angle. Personally, I think it looks a little bit less. And so, I might graph what happens at 0, somewhere like maybe down there. Just a little bit less than 1, just to guess. Your guess is as good as mine. Somewhere around this next point here, it looks like a tangent to the curve is more or less horizontal, and a horizontal line has a slope of 0. So somewhere around that point there, we get that the derivative is equal to 0. And then if you move to the right a little bit further and you sketch a tangent line and estimate its slope, well, now we've got a tangent line with a negative slope. It's decreasing as you go from left to right. How steeply is it decreasing? Well, a slope of -1 would be at a 45-degree angle. That doesn't look quite that steeply decreasing. And so I would say, something, maybe -3/4 or something like that. And so somewhere at that x value, I'm going to say that the value of the derivative is somewhere around there. I'll just do a couple more. I've moved a little bit further to the right, and I see that a tangent line appears to be negative, but a little bit more steeply negative, and so maybe closer to -1, so somewhere around there. I've got a slightly larger negative number, larger in magnitude negative number there. And I got impatient and did 3 more rapidly, but that's this point here with a tangent line here, so that's some negative number, but a less steep negative number, so a smaller negative number, so something like, I don't know, maybe that. And then I did this point here where it looks like a tangent line is once again horizontal, so somewhere over there the derivative is 0. And then interestingly, move on just a little bit further and the tangent line becomes positive again, a small positive number, less than 1, and so something like maybe that again over there. And then what do you do with all this information? You string it all together into your best guess at a sketch of what the derivative looks like. And that's all there is to it. You are picking points, estimating tangent lines, and then using the slopes of those tangent lines to give you the values of the derivative at those points. And so what will happen on your homework is they'll show you, some graph and then probably give you some choices. Is it this graph? Is it that graph? Or is it that other graph? Probably what you should do is take a look at the graph, take your best sketch of the derivative, and then see which one it looks the most like, and then that's probably right. Okay, you are now all set to do the differentiability homework. Stupid pet tricks thrown in just for good measure. Have some fun with it. See you in class.